So we're going to apparently radically shift gears and start talking about sequences and series in this class. And it seems like a radical departure from the topic of functions, but actually it's very important. As we'll see, we can describe functions with what's called a Taylor expansion. Okay, so you could describe functions, a certain class of functions, as polynomials. You can approximate them as a sum of polynomials, and this you could even get exact expressions for infinite sum of terms of these polynomials. And so this topic does intersect with functions in a very serious way, and that's why we are discussing sequences and series in Calc 2. So we'll start with just an overview of what sequences and series are, and then we'll tackle each concept separately. Okay? So what is a sequence? A sequence is basically an ordered list of numbers. Okay? So it's an ordered list. Okay? So you can't just flip around the numbers. And the numbers can repeat, so you can get 1, 1, 1, 1, for example. That is an ordered list, and those are separate terms. Okay? And we could generate this list, a sequence. We could generate it in several ways, depending on the list. One way to generate a sequence is with a recurrence relation. Okay? So many people in programming might have run into something like this, where you basically start with the nth term to get the n plus 1 term. So you do something with the previous term to get the next term, okay, where n is from 1 to 3, okay? We could even start counting from n equals 0, that's fine. We may also get a sequence by an explicit formula, okay? We explicitly define the sequence as a function of n, okay? So if we want the nth term, we have this function of n, not of a sub n minus 1, right? But that would have been a recurrence relation, but just an explicit formula of n, and we'll see some examples of that as well. Okay, so that's called an explicit formula. And we can actually view sequences as functions from the integers, okay? And if the numbers are real, then it's a function from the integers to the real, or the whole numbers or natural numbers to the reals. Okay, that's one way of viewing a sequence. So each number in a sequence is called a term. So each one of these is a term, and this subscript that we have as n over there, that's called the index. Okay. To index which term we are talking about. So let's look at an example. Now consider the following sequences. Okay, and you can see the notation here. Quick note on the notation. So with these curly brackets and this a sub n, it defines, that's a way of saying the whole list. Sometimes you also see something like this, where you're going from 1 to an infinite number of terms. Okay, and so that's just a different notation. So for these two sequences, we want to, 1, find the next two terms. We want to find the recurrence relation that generates that sequence, and we want to find an explicit formula. Okay. So let's start with a sub n. So -2, 5, 12, 19. Well, you are seeing a pattern there, and it's that you're adding 7 to each of the previous terms. Okay, so the next two terms will be 19 plus 7, which is 26, and then 33. So we could add 2 more terms of 26 and 33 to that. To get a recurrence relation, what are we doing to get the next term? We're taking the previous term and adding 7 to it. And we start with the 0th term, okay? And again, we decided to start with n equals 0. We could shift around and play with that a little, and we will for some of the problems. But here, we're just going to start it at n equals 0. And we'll set that to -2, okay, the first term there. And so each subsequent term is the sum of the previous term plus 7, starting at n equals 0, which was -2, and that will generate that whole sequence. What about an explicit formula? Okay, so if we start again at n equals 0, then you could check that, we are increasing by 7 each time, so we get that 7n, and that -2 shifts us to where we want to start. Okay, so n equals 0, we do get -2, and then for n equals 1, you just plug in 1 right in there. 7 times 1 minus 2 is what? Is 5. Okay, and you could see that you'll generate all of these terms. What about for b? 3, 6, 12. Again, we're seeing a common pattern here, that each one is double the previous. Okay, so you take the previous and you multiply by 2. So 48 times 2 is 96, and then 96 times 2 is 192. And so we would get 96 and 192 if we continued. Okay, and now if we want a recurrence relation that will generate this sequence, we start at b naught equals 3, and we just take the previous term and multiply it by 2. And here we have n starting at 0. What about if we wanted an explicit formula, one where we could just plug in the n and not worry about what the previous term was? Well, here, this should work. Okay, n equals 0 again, you'll get 3. So we started it out right, and then we have this 2 to the power n because we're multiplying by 2 every iteration. And so this is an explicit formula for that sequence for any n, and you don't even need to know the previous term. So a rough definition here, okay, and we will give a more formal definition and even a very formal definition later on, but just to sort of build an intuition, if the terms of a sequence approach a unique number L as n increases, that is, if an can be made arbitrarily close to L by taking n sufficiently large, then we say that the limit of the sequence a sub n as n goes to infinity is L, that it exists, and that the sequence converges to L. If the terms of the sequence do not approach a single number as n increases, then the sequence has no limit, and the sequence is said to diverge. Okay, we say diverges if there is no limit, so it could be oscillating between numbers. It could also just keep increasing without bound. And so in these situations, we say that the sequence would diverge, whereas if it approaches a number as you keep getting farther and farther out, we say that it has a limit and that it converges. Okay, and this is going to be a very important concept, the concept of sequences converging, and we'll spend a lot of time on that. Okay, so let's take a look at an example. Write the first 4 terms of each sequence. Make a conjecture on the convergence and limit. Okay. So A, we have this sequence here, this -1 raised to the power n, starting from n equals 1 to infinity. And we have this over n squared plus 1. So -1 to the power n over n squared plus 1 going from n equals 1 to infinity. So let's write out the first 4 terms. Again, this is an explicit formula, so all we have to do is just plug in wherever we see an n for the first term, we'll just plug in 1, and we're starting at n equals 1 there. It tells us that. So we'll get 1 squared plus 1 on the bottom there and raised to the power n. For the second term, we get a 2, and then 2 squared plus 1, and likewise for 3 and 4, and we get these values there. Okay. Now notice that we are getting oscillatory behavior here, and we get a negative value here, and then positive value, and a negative value, and positive. But at the same time, this is getting closer and closer to 0, so we can conjecture that the limit of this sequence is 0. Okay, and here we're just sort of, again, we're going to develop some formal tools to be able to make definite statements about these, but let's just take a brief overview and sort of see where we're headed. B, we have this sequence over here, cosine n pi. And again, plugging in n equals 1, because cosine pi, cosine 2 pi, and we just, wherever you see an n, you just plug in the value for that term. So here's the fourth term. We just plug in 4 for n. And we're getting minus 1, 1, minus 1, 1. No divergence, no divergence in the sense that it's not growing without bound, but it keeps oscillating. It's not really going towards any one value. So this limit diverges, okay? This sequence diverges. There is no limit there, okay? You're not approaching 1 and you're not approaching minus 1. You keep flipping around. And so this sequence diverges. What about this? A sub n from n equals 1 to infinity, that just sort of is very basic there in general, but here's where it gets defined. So we get a recurrence relation, and we start with a1 is equal to 1, so we're starting from n equals 1. That's 1. And then what do? We take the previous term, multiply by negative 2, then take the previous term from that and multiply by negative 2, and you do that, you'll get 1, negative 2, and then multiply that negative 2 by negative 2, and you get 4, and then take that 4 and multiply it by negative 2, and you'll get negative 8. And not only is this oscillating, but it's also growing without bound, and in both directions, in the positive direction and in the negative direction. Okay, so the even terms are growing in the negative direction here, so the second, the fourth, and the odd terms, the first and the third, is growing without bound in the positive direction, and so this appears to diverge. Okay, so we got sequences, and let's now start talking about infinite series. Okay, sequence, you get this infinite list of numbers, okay, these terms. So given that sequence, the sum of its terms, a1, a2, a3, you just keep summing all the infinite number of terms there, is called an infinite series. Okay, it kind of sounds weird that you're summing an infinite amount of terms, but again, we've been doing integrals, and that's basically, we should be kind of comfortable with dealing with the infinite now. The sequence of partial sums, S sub n, so this is a sequence associated with the series. This series has the terms. So S1, S sub 1 is the first partial sum, and that just involves the first term. S2, you're adding the first two terms. S3, you're adding the first three terms. Sn, you're adding the first n terms. And in general, this is a formula for S sub n. Okay, so you're going from k equals 1 to n. You're adding the first n terms, where n is being, where the index starts at 1. Okay, now this is a very important concept. Okay, the concept of partial sums, the sequence of partial sums, is super important. Why? Because it allows us to frame the problem of adding an infinite amount of terms as a limit with sequences. Okay, so we're getting, notice, although each one of these is sums, and so you're getting an infinite series if you're summing the infinite terms, that's what happens when you take the limit of this sequence of partial sums. Okay, so that's our strategy for tackling the idea of adding an infinite amount of terms. It's going to be taking the limit of the sequence of partial sums. So we frame the language of series in terms of sequence by using the concept of partial sums. And then we know how to work with limits of sequences, and we'll get much more familiar with that. But once we're familiar with working with limits of sequences, then summing the infinite amount of terms will look like taking the limit of the sequence of partial sums. Okay? So if the sequence of partial sums has a limit, the infinite series converges. Okay, so you could think about, that's what happens when you add an infinite number of terms. You just take the limit as n goes to infinity. That means you're adding the infinite amount of terms. Okay, and again, this is a sequence. So we'll say the series converges to that limit, and we write that this term here, which is summing to infinity, okay, similar to kind of how we did it with integrals, we'll take the limit as n goes to infinity of the partial sum, okay? And we'll get a limit for that, and that's going to be the meaning of adding an infinite amount of terms. If the sequence of partial sums diverges, the infinite series also diverges, okay? So if the partial sums is growing without bound or is oscillating, then it diverges. So again, that was the advantage of using the concept of partial sums, and we're able to frame the topic of adding things together as a sequence, okay? Consider the infinite series that you see there. Find the first 4 terms of the sequence of partial sums. And then B, find an expression for Sn and make a conjecture about the value of the series. So all right, we want to get the first 4 terms. So the first one, S sub 1, we just have one term, so it's sort of a trivial addition. Okay, you just state it. Now what's S2? Please don't just plug in 2 in this formula. That's what the second term would be, but not the second partial sum. Second partial sum, you got to add the first and second term, okay? And you'll get 2/3. What about S3? Again, please don't just plug in 3 in there. That's going to be, again, the third term. No, the third partial sum, you got to add the first 3 terms together. So there goes our half from the first. There goes 2/3 there for, or 1/6 for the second term. And 1/12 is going to be the third term. Okay, so 1/12 is what happens when you take 3 and you multiply it by 3 plus 1, which is 4, so you'll get 1/12. Okay, and so you'll get 3/4. You could have also looked at this as S2 plus the third term. Okay, and S sub 4, you add the first 4 terms and you get 4/5. And again, speculating, it seems like S sub n is equal to n over n plus 1. It seems like we have an explicit formula for this sequence of partial sums. Okay, again, this is what you would get if you add the n terms. Okay, it seems like you're getting that formula there. And so we'll conjecture that. And if we take the limit, so if we want to add all of the infinite terms there, we just want to keep adding these terms. How do we do that? We'll take the limit as n goes to infinity of the partial sum to n, which we'll plug in as our conjecture, n plus, so that should be equal to n plus n over n plus 1. And so we should be getting that if we keep adding an infinite amount of terms, okay, we're going to approach 1. Okay, that's the limit. You never quite approach it. I mean, you'll have like trillions and trillions of numbers, and it keeps getting closer and closer to 1. Okay, but the limit there is 1. So let's look at another sort of common example. It's using the concept of series and sequences for fractions. Okay, so consider this infinite series where you're just adding these terms here with 9, with more and more zeros in front of the 9, so more and more decimal places where you put the 9. And each term is 1/10 of the previous term. So 0.9 times 1/10 is 0.09. And then the next term there is 1/10 the previous, and so on. Find the sum of the first 1, 2, 3, and 4 terms. Okay. So again, the partial sum. S1 is 0.9. That's a trivial addition. S2, we add the first 2 terms, we get 0.99. S3, we add the first 3 terms, and we get that. S4. Okay. And you see where this is going. It seems like Sn is going to 1, right? You keep going 0.9999, keep having 9s there, you're headed towards 1. And indeed, if you take the limit of the sum of the partial sum, okay, which is just taking the limit of a sequence, then we should get 1 there. Okay, and here we framed, we wrote out the explicit formula for these, and we should get 1. And again, we'll make this more concrete and actually work with formulas that would give us this result exactly. And so we'll end our brief overview of the concept of sequences and series with comparing and contrasting them with functions, what we've been working with before. So for a sequence and series, the independent variable is n, okay, this integer. For functions, it was typically x. Okay, the dependent variable, so is going to be f of x. That's the dependent variable which we typically associated with the y. And here we have a sub n, okay, which you could sort of view as a function of n. Okay, just like this is a function of x, this is a function of n. The domain for a sequence to series is integers. For functions, it's the real numbers. The accumulation for sequence and series is sums. You're adding terms together, okay? You're dealing with integers in the domain, so you're adding these terms. On the other hand, the accumulation for functions was integrals, okay? So you're getting an area. Accumulation over finite interval, we use that symbol there. And for functions, it's the integral there, okay? That's over a finite interval. And then over an infinite interval, we have, we just have that infinity there, which again, how would you sort of work with this is that you would have that limit as n goes to infinity of the partial sum, okay? That's how we would do it. Here, how we did it here was we took, this was the improper integral, and so we took the limit, okay? And so we're tackling these concepts similarly, okay? At least as far as the analog with the notation.